Okay, this is the final lesson for week 1 of the online trig class. 7.3, computing the values of trig functions of acute angles. We're going to be looking at some special angles that remember showed up on our unit circle. Those were 30 degrees, 60 degrees, and 45 degrees. Each of those has very special trig ratios that are going to pop up over and over again in our class, so it's very important that you pretty much get so familiar that you have these memorized. They will also be part of our unit circle, and we will use that over and over again throughout the whole class. So find the exact values of the trig functions of pi over 4, which equals 45 degrees. So in the triangle below, the measure of the remaining angle, so let's look down here. If you have a triangle, your triangle has to add up to 180 degrees. So if this is 90 and this is 45, this has to also be 45 degrees. So that's that angle right there. The length of the remaining side would have to also be the same as this, because there's something interesting about triangles, and this is another one of those facts that we just kind of assume that you remember from a geometry class. Side length corresponds to how open the angle is. So if two angles open up exactly the same amount in a triangle, that's related to having the same side lengths. So that means that this is actually what we call an isosceles triangle. So that would have to be 1. And then we can use Pythagorean theorem to find the hypotenuse. So 1 squared plus 1 squared equals c squared. That would be 1 plus 1 equals c squared, or 2 equals c squared. So c equals the square root of 2. So there we have that. Now that we know that, we can define all of the 6 trig functions for this special 45, 45, 90 triangle. So in a 45, 45, 90 triangle, sine of theta, cosine of theta, tangent of theta, then we'll also need cosecant of theta, secant of theta, and cotangent of theta. So we're going to focus on the top 3 first. Sine is, remember, opposite over hypotenuse, so that would be 1 over the square root of 2, which, remember, we need to rationalize, so multiply top and bottom by square root of 2, and you actually end up getting square root of 2 over 2, because remember, this would become a square root of 4. Cosine is identical because adjacent is also 1 and the hypotenuse is still square root of 2. So that's just going to end up being another square root of 2 over 2. Tangent's opposite over adjacent, so 1 over 1 is just 1. And remember, we flip all of these to get our reciprocals down here. So I always flip from the original ratio, not this version. So this would just be square root of 2 over 1, so that's square root of 2. Square root of 2 over 1 again, so that's square root of 2. And 1 over 1 again, which would still be 1. Now the 3 we are going to care about the most, obviously, are the sine, the cosine, and the tangent. Those are the ones that are going to pop up on our unit circle when we fill that in later. Now we want to talk about 2 other special angles in a triangle, pi over 6, pi over 3, which both relate to 2 different degree measures of 30 degrees and 60 degrees. So this is related to a 30, 60, 90 triangle. So it says find the exact values of the 6 trig functions of this triangle. So we need to manipulate this triangle to find the measure of side A. Okay, so the problem with this triangle right here is that we know only one of the sides, and without knowing the relationship of how the 30 degree and 60 degree angles are related to this side they've listed over here, you really can't go any further. But there is something we can do. We can create a mirror image or reflection of this triangle on the other side. And I'll show you why I do that, because this would then also be 2, and this would be 30 degrees. That means that this is 60 degrees. 60 degrees and 60 degrees is 120. I'm talking about this now big triangle. I'm going to outline this in blue. My blue triangle. Okay? And that means this has to also be 60 degrees because that would be a 180 degree large triangle. The reason I wanted to point this out is that this is also A. in a 60, 60, 60 degree triangle, you're equiangular, equilateral, which means all of your angles are the same, so they're all 60 degrees, and all of your sides are the same. So what that means is that A plus A equals 2, because this and this have to equal the same as these. So that means that A is actually 1. Okay, so let's redraw just the 30, 60, 90 triangle. So we use the fact that we could draw this equilateral, equiangular triangle based off of the fact that when you mirror this, you get the same degrees here, same measurement here, and that allowed me to solve for this missing angle here and this missing piece. So this 30, 60, 90 triangle, we now know that if this is 2, this is 1, because each side over here, each one of these is 1, and that will allow me to solve for this missing piece here. So for side B, we would have 1 squared plus x squared equals 2 squared. 1 plus x squared equals 4. Subtract over the 1 and you get 3, and so x equals the square root of 3. So now we know in a 30, 60, 90 triangle, the side across from the hypotenuse is 2. The side across from 30, or the smallest angle, is half of this hypotenuse, so it's 1. And 60 is always this number times the square root of 3. So you don't actually see that there. They don't put in all of the variables, but this ratio means that even if this was 4, I could still find the other two sides. If this was 4, this would be 2, and this would be 2 on the square root of 3. It has that proportional relationship. So once we have defined the 3 sides of the triangle, now we can talk about the trig values. And let's see, does it specify which way we're going? Well, we can do it for both. So if we want to know sine of, let's say, I guess I could start with, because I didn't write this on these, by the way. I'm going to come back up here, and I just realized I didn't write this. Each of these was for 45 degrees. So I didn't write my angle in, but I'm going to have to do that on the next group because the angles are different. So because both of these were 45, these ratios held for both sets. So for this case, we're going to do it once where we find the 6 trig ratios for 30-degree angle, and then we'll do the 60-degree angle. But remember, there's complements there, so there should be, if we use that property, there should be some similarities. So we're going to do sine of 30 degrees, cosine of 30 degrees, and tangent of 30 degrees. And I know you guys can flip to get cosecant, secant, and cotangent, so I'm not going to write those. I'm only going to focus on sine, cosine, and tangent. So sine of 60 degrees, cosine of 60 degrees, and tangent of 60 degrees. And I'm going to put a note over here. Still need to find cosecant, secant, and cotangent of each. But the main thing is those are just flipping fractions. So if you can find these, you're good. So sine from 30, that means that we're referencing this angle. So in this case, all of these are yellow. So for sine of 30, opposite over hypotenuse would be 1/2. Adjacent would be square root of 3 over hypotenuse, square root of 3 over 2. And tangent is opposite over adjacent. And we will have to rationalize that one. So that would be times by square root of 3 over square root of 3. So that is square root of 3 over 3. So there's my 3 different ratios for sine, cosine, and tangent for 30 degrees. Now here's the cool thing. Remember, we just learned about complementary angles. So sine of 30 should be the same as cosine of 60 because remember, they're opposite complementary functions of each other, and they add to 90 degrees. So this is actually 1/2. I can double check that though, because remember, cosine is adjacent, which is the one connected to it for the leg, over hypotenuse. So sine of 60 should be cosine of 30. And then we can't do anything here because I didn't find cotangent, but I can find tangent of 60 pretty easily. So that would be opposite over adjacent, which is square root of 3 over 1, which is just square root of 3. It was just the reciprocal property. Okay, so let's see what else we have. All right, so we're going to fill in this chart, and we're almost done with this set of notes then. So remember, we want to, this is going to help us with our unit circle that we're going to be focused on in one of the next sessions. So pi over 6 is 30 degrees. Pi over 4 is 45 degrees. Remember, you can use your multiplication of 180 over pi to help you figure this out, and then pi over 3 is 60 degrees. So those are those three special degree measures we just studied in our triangles. And what we learned is that, and you can go back to your page before, we learned that sine of 30 degrees was 1/2. So I'm going to show you, we just found that right up here. Okay, sine of 30 degrees is 1/2. And that meant that cosine of 30 degrees was the square root of 3 over 2. Tangent of 30 degrees was square root of 3 over 3. Or remember, that also started out as 1 over square root of 3. That's what it was before we rationalized it. Cosecant would then be 2 over 1. Secant would be 2 over the square root of 3, which is rationalized would be 2 square root of 3 over 3. And cotangent, we flipped this guy right here, so that'd just be square root of 3. For 45 degrees, we noticed that sine and cosine were identical. Before they got flipped, remember it was 1 over the square root of 2, and then we rationalized it. So this was square root of 2 over 2. Tangent was 1. Cotangent, when you flip 1, you still get 1, and when you flipped both of these, you got square root of 2. For 60 degrees, we realized that sine and cosine flip-flopped since that added to 90, so this is square root of 3 over 2. This is 1/2. The tangent was square root of 3. And then we haven't flipped these yet, so this would be 2 over the square root of 3, which would be 2 square root of 3 over 3, and 2 over 1, which is just 2, and this one would be 1 over the square root of 3, which if we rationalize comes out as square root of 3 over 3. So out of all of this, sine, cosine, and tangent are going to be the most important, but it's good to make sure you can find the ratios quite easily. Okay, so we want to find the exact value of each expression, and we can use what we know in this, what we've just learned. So remember, sine of pi over 3, in case you haven't memorized them yet, you do need to memorize them, but right now I understand you haven't. So sine of pi over 3 is square root of 3 over 2, so we're going to replace that in there. And it says we're squaring that. Plus tangent square root of pi over 4, so tangent of pi over 4 is 1, and we're going to be squaring that. So if we square this, a square root squared is just the number, so that would be 3, and 2 squared would be 4. 1 squared is just 1. We can get a common denominator of 4 over 4 for 1, and that makes this 7 over 4. Sine of 60 degrees, remember 60 degrees is the pi over 3 one again. So this is square root of 3 over 2. Cosine of 45 degrees, so that would be square root of 2 over 2. And notice this has nothing between it, so that means we're timesing. When you multiply radicals together, you multiply the insides, so that would be square root of 6 over 4. Cosine of pi over 3 is 1/2. Cotangent of pi over 4 is 1. 1/2 minus 1 is negative 1/2. So see, now that we have some ideas about these special angles, we can do some evaluations. Okay, so a lot of what's going to be left in this section of notes is application problems. Oh, sorry, this wants to always move too fast. So it says use a calculator to approximate the value of a trig function of acute angles. So if you don't have the special angles of 30, 60, and 45, there are buttons on your calculator that will allow you to work them out. That's why you have a scientific calculator. So what we need to do, and depending on how your calculator works, you'll have to test this. Some calculators you have to enter in the degree first and then type in the cosine or the sine. Some of them you have to enter in the cosine or sine first and then type the degree. Most of them you type in the trig part first and then the degree. But for my calculator on this computer, I can't do that. It works backwards. And you do need to make sure your calculator is in degrees, not radians. See how that switched to radians, and that will matter. So this is in degrees because this is in degrees. So this is 15 because mine works backwards. And then I want cosine of that. So it looks like I have 0.9659. And they said only go to 2 decimal places, so 0.97 because the 5 will bump the 6 up. So this is approximately 0.97. Be careful with this next one. A lot of people want to stay in degrees. Note that there's no degree symbol. If you don't have a degree symbol, use radians. So I'm going to be doing secant of 10, but I want to make sure I'm in radians. Now for me, I don't have a secant button, I don't think. No, I don't. So some calculators might have that button, most of them don't. So we need to think about the reciprocal of secant. Secant is 1 over cosine of 10. So my easiest way of dealing with these is to do the reciprocal of those. So 1 divided by, oh, and I need to make sure I'm in radians, so there's my radian switch. And then in my calculator, I'm going to put a parentheses to tell it I'm working on the bottom. And then again, I have to enter in the 10 first, and then the cosine. Most calculators will enter in cosine first, then 10. And then I hit enter, and this would be negative 1.19. The 1 does not bump up the 9. Okay. Let's look at this application problem. From a distance from A to C across the gorge illustrated in the figure. Okay, so we have this picture. So we're going to find that distance from A to C. So we're looking for this. And actually, let's do that in a different color. There we go. All right, so I know that this is 35 degrees. So that can be my theta. And I have the length of the adjacent side to that angle, and I'm looking for the height. So I'm going to think, using SOHCAHTOA, which one uses adjacent and hypotenuse, and it is cosine. So cosine of my angle, 35 degrees, equals the adjacent, which is 100, over the height. Now you can think of this as being over 1, so actually we're going to cross multiply. So I get x cosine of 35 degrees equals 100 times 1. And so to solve for x, I actually have to divide the cosine of 35 degrees over. So on my calculator, I need to do 100, and I need to go back to degrees, so see, you have to pay attention to that, divided by, open a parenthesis since it's in the denominator, and for me I have to type in 35 and then tell it to do cosine. So that is 122.08. And this is being measured in feet. Now you should check to make sure that makes sense. This is the hypotenuse, so it should definitely be longer than this leg, and it is. Okay, meteorologists find the height of a cloud using an instrument called a ceilometer. I can't say that right. Celiometer. It consists of a light projector that directs a vertical light beam up to a cloud base and a lie detector that scans the cloud to detect the light beam. On December 1st, 2000, at Midway Airport in Chicago, they had a base of 300 feet is what they were using. I'm not going to say it again because I'll say it wrong. And it was employed to find the height of a cloud cover. If the angle of elevation of the light detector is 75 degrees, what is the height of the cloud cover? Anytime they have a lot of wording or there's objects or things like that, you want to draw a picture. So we're trying to have an angle of elevation. That's usually where I start. So that means we have some flat line, and at some point there is an angle that goes up from the ground, okay? And we know that that is 75 degrees, and that is from the light detector. Let's read what else we have. The object, so it projects a vertical light beam up to the cloud base and a light detector that scans the cloud to detect the light beam. So we need to have a place where there is a vertical thing. So here's my cloud up here. Ooh. This is the vertical light beam that they were talking about. Anytime something is directly vertical to the ground, that gives us a 90-degree angle. And the other thing we were told is that the base of this instrument is 300 feet. So that means that this is our whole instrument down here, and it is 300 feet long. And what we want to know is the height of the cloud cover. Okay, so we're looking for the height here. So it looks like we have opposite to our angle, and we have adjacent to our angle. Here's our theta right here, and that sounds like TOA, because that's opposite over adjacent. So we're going to use tangent of 75 degrees equals the height that we're looking for over the length of that adjacent piece. So to solve for this, we need to multiply both sides by 300. And that would be 300 times, parentheses, 75 tangent, and I am in degrees. Always double check that. And that is 1,109.62. And 19.62. Sorry, I might not have said all of the numbers before. So it says that that cloud is over 1,000 feet in the air, so 1,119.62. Okay, so our final example says to measure the height of Lincoln's character on Mount Rushmore, two sightings 800 feet from the base of the mountain are taken. If the angle of elevation to the bottom of Lincoln's face is 32 and the angle of elevation to the top of his face is 35, what is the height of Lincoln's face? Okay, so I am not a good drawer of people. There's my Lincoln. Yay! So there's his face on the mountain. And we know that from the base of the mountain, two sightings 800 feet away from the base are going to be measured. One goes all the way up to the top of the head, and the other goes to the bottom of the head. The one that is on the bottom of Lincoln's face, we said measures 32 degrees, and the one that goes up to the top only measures 35 degrees. Now that 35 does include the 32, so that means there's an extra 3-degree split right here. This would be 90 degrees because we're assuming that this is flat to this vertical here. And we want to know the height of his face. So we are looking for, if you connect this, so we're assuming his face lies flush. I should draw that a little bit better. So we're looking for this height right here. Okay. Now, how are we going to do this? We have to think about what we know. We could easily find the height of this because I know that this is 800 away and I know this angle is 35, and this would be the, just like what we did a minute ago, this would be the opposite over adjacent. So if I take tan of 35 degrees, which is this full angle right here, that would give me h over 800, because that's the length away we are from that that vertical line. So 800 times tan of 35 degrees equals h. So 800 times 35 degrees tangent. That's 560.17. And that's in feet. Okay, so we can employ a similar tactic to help us find the measurement of this other part, which is from, now we're not going to be able to find x directly. That's not going to come directly. If you think about this being height 1, we can also measure the smaller triangle and find height 2. If you know height 1 and height 2, you can subtract to get x. So let's call this height 1 to distinguish that. So tangent of 32 degrees, because that's the smaller triangle that's created here, would be height 2 over 800. So that's 800 times tangent of 32 degrees. And if we work that out on our calculator, so 800 times 32 tangent degrees is 499.90, because that would round up. 0.90 feet. Making sure, yes. Okay, so that means that our blue part right here, which is the actual height of Lincoln's head, is going to be related to height 1 minus height 2. So we subtract those two. So 560.17 minus 499.9 is 60.27. So according to this word problem, Lincoln's face on Mount Rushmore is 60.27 feet tall. That's a pretty tall face. So that ends the section 7.3 notes, which that should be everything for the week 1 in our My Math Lab and our calendar. I hope you enjoyed these videos, and there'll be more to come each week.